We're going to start with implicit. It's the same. What do we have to think of when we're doing implicit derivatives? Anybody have any idea? Usually it says leave in implicit form. Don't worry about writing it down. You can if you want, but I'll talk about a little bit more about what that means briefly today, but all of these ones we're leaving in implicit form, trust me. What do we have to think of? Implicit derivatives are tricky because it looks really simple, and then in fact it's not. It's more complex. Like if we look at this first part, what do we have to do to take this derivative? So that was one of the things. When you take the derivative of y, it's dy by dx. That's a big part of implicit differentiation. Good. What else, though? What's tricky about this one? It's product rule, because it's a function times another function. Even though this has a y in it, it's still a function, so this is product rule. So we're going to go derivative of the first thing times the second thing plus derivative of the second thing. Look, folks, no exponent. So we go straight to the trig. Derivative of cos is negative sine. Angle doesn't change. Times the derivative of the angle. Derivative of y is dy by dx. If that was just cos x, you are still taking the derivative of x with respect to x, but it's 1, so we don't write it. And this is a trick. People think, well, it's just y. But the derivative of y is dy by dx. Okay? Times the second thing. Sorry, times the first thing. Don't forget your x squared. And then I go on to that was just that first part there. So now I take the derivative of this. We often see derivative of sums. It's fairly easy. So no exponent. Derivative of sine is cos, so minus cos. Angle doesn't change. Times the derivative of the angle. It's a sum, so we just do each part separately. So it's going to be good. Equals 0. I'm going to take a few extra steps to clean stuff up here. Oh, actually, no, I'm not for this one. I'm going to move this over to the other side. Now we're trying to isolate for dy by dx. That's what the instructions say. Find dy by dx. You have to isolate for dy by dx. So I'm taking this dy by dx term and this dy by dx part, and I'm going to move this to the other side. And at the same time, I'm going to expand this. This is cos x plus y times 1 cos x plus y times dy by dx. See that? So I've got to expand that. So I've got negative x squared sine y dy by dx minus cos x plus y minus cos x plus y dy by dx equals negative 2x cos y. This term right here is that times 1. I've got another term here that does not have a dy by dx, so I'm going to move it over. And I'm going to factor out the dy by dx. Is it okay if I do that all at once? So dy by dx, negative x squared sine y minus cos x plus y equals cos x plus y minus 2x cos y. Whew. Then I just divide. Any questions? This is in implicit form because it's got x's and y's. What if you were required to leave it in non-implicit form, explicit form? What would that mean? That would be the alternative, leave in explicit form. We never leave it like this. We're always solving for dy by dx. Leave in implicit form means I'm allowed to have x's and y's. If I wasn't allowed, if it had to be explicit, I would have to solve that for y to figure out what y is, get some expression y equals, sub that in to all the y's in the derivative below. How the heck do you solve that for y? You can't. So in trig, we never really do. We will in logarithms. So for now, don't worry about it. For now, we always leave in implicit form because otherwise, like we couldn't not do that. Okay? I think you can try the left side of this equation. The right side is a little bit different. Can't remember if there was an example like this in the homework last night. There is tonight. You can try the right side as well. It's not that bad. No product rule here or anything like that. Okay, take a look up here for a minute. This reminds me of something I forgot to point out in the learning goal. So I'm going to flip back over. Some people did this. Like, what's happening here? What is this even saying? Huh? Sine x is the angle. What some people did in the learning goal is somehow they took an angle out and they ended up with just like a sine of nothing. And this happens in MHF a little bit too, but like I saw a few people do that here where all of a sudden the angle disappeared and it's like, what happened here? Be mindful, like think very carefully of what the angle is. You can't pull that out. I kind of made a comment, you can't factor out 5x here or anything like that, but like you can't remove this 5x or remove this x or something like that. That cannot happen. So this is not cos times sine x. It's cos of sine x. So how do you take the derivative of that? You just go through the steps. So there's no exponent. I don't have to worry about that. So derivative of cos is negative sine. Of the angle. Again, this gets even harder because the angle is the trig thing. So negative sine of the angle, which is sine x, times the derivative of the angle, which is cos x. Again, it looks like I'm missing an x here, but I'm not because that's the angle, so be careful. Okay, so I'm going to expand on this side. I'm going to write it in this order just because I think it's maybe clearer? I don't know. Maybe not. Okay, move everything over and then divide, and then we're done. Any questions? Just imagine a question like this. Let's see. Cos cubed of sine squared of 3x squared. Okay, so I would do the exponent, and I'd get 3 cos squared of the angle. Then I would do the trig, which would be negative sine of the angle. Then I would do the angle, which would be exponent, then trig, then angle. And I would have like, holy cow, I've never seen a question like that. You might have just an exponent, but I've never seen it go that far. You could keep going too. What if this was like tan or something like that? Oh my gosh. One question. The whole test is one question. Can you take the derivative of this? All right. So what we're doing today is properties of these things. Find the critical points, intervals of increase and decrease, local extrema, same thing. Then points of inflection and intervals of concavity. In other words, we're going to do a first derivative chart, then a second derivative chart. And this is just practice to start sketching tomorrow. Nothing special about trigonometry that we always do a first derivative chart and a second derivative chart. This is just for practice to see what each of them is like. Generally speaking, if you are asked to sketch, a full sketch would be a second derivative chart. You do it the same way we were doing in the last unit. This is what I mean by nothing new. But this is going to amalgamate a lot of skills that you have learned this year in MHF, all the way up to the previous unit of calculus. Yeah. Well, cos x, the derivative of cos x is negative sine, and the derivative of negative sine would be negative cos, because... Okay, so if we were doing a full, we would probably do derivatives first like usual, but if we were doing a full sketch, we'd also get intercepts and all that good stuff. We're not doing that, so we can go straight to the first derivative. Everybody okay? Got this copied down? So derivative of cos is negative sine. And again, derivative, there's no exponent here. So derivative of cos is negative sine. This is going to be, plus sine 2x times the derivative of the angle. So times 2. I'm going to clean this up a little bit. I'm going to take a few steps. You could do this absolutely in one step. I'm going to take a few. So I'm going to bring the 2 out front. Actually, this one maybe is going to be quick. 2x minus sine x. When we do a first derivative chart, what do we have to do? To find our intervals, to actually write the chart. we got to set it equal to 0 or does not exist. So you can either do that now or you can do it after. In fact, I'll do it now. Usually I would probably, just like we did in the last unit, do all the factoring, get it into a form I like early on. But because we're reviewing all this MHS stuff, let's do it now. So critical values when y prime equals 0 or does not exist. Y prime exists everywhere. Is there any reason for it not to? There's no asymptotes, not dividing by 0 ever. Tangent has asymptotes because it's sine over cos. So whenever you're dividing by cos, when cos is 0, you would have an asymptote. We're not really going to see a lot of tan though, so don't worry about that. So generally speaking, these will exist for all x, but we do need to say that every single time. So y prime equals 0 when 2 sine 2x minus sine x equals 0. And from MHF, how do we solve that? Do you remember solving trig equations? It's one of the hardest things you do in all of MHF. And if I have to solve for the intercepts, I'm doing it once with the original equation. If I have to find critical values, I'm doing it again for the first derivative. And when I have to find points of inflection, I'm doing it a third time with the second derivative. So you're going to be solving 3 trig equations when you do a sketch for these things. We're going to use, not necessarily, but we can't just turn cos into sine. But you're right, we're going to do that kind of thing. We're going to put it in the kind of situation where we can factor it or something like that. You can't typically solve if you have a double angle and a single angle, especially when you're adding like that. That's not going to happen. So absolutely we're going to use an identity to get rid of that double angle. What is sine 2x equal to? Good. I think we saw that yesterday, didn't we? So 2 times, this is the one where you could do more work here maybe. 2 sine x cos x minus sine x equals 0. I'm going to put these together. 4 sine x cos x minus sine x equals 0. Now what do I do? Never move the sign to the other side and set them equal to each other. That is not how we solve this stuff. Nicely done. We can factor out a sine x. So this is that common factoring type for cos x minus 1. Therefore, sine x equals 0 or 4 cos x minus 1 equals 0. Cos x doesn't equal 1 minus sine x, so you would be changing the question by quite a lot. Sine squared x equals 1 minus cos squared x. What do we do now? Yeah, where does sine x equal 0? 0. Is that all? Done? Pi? Two pi. What do I do with this one? Rearrange, thank you. This is not a special angle. It grew up and its mother told it it was special, but it's not true. Everybody's told they're special, they're not. So how do we do that? Yeah, shift cos. So I'm going to write that out just to remind us. So x equals cos. Remember we talked about this yesterday, how that's like a unclear notation, but the inverse cos, and that works out in radians. Make sure you're in radians to 1.3181 if we do 4 decimal places, I think. Okay. Oh, that's x related. That's x related. So now what do we do? Seema? Say that again? Why? Is it? How do you know that? Good idea, though. This is what we're doing next year, right? Yeah, so we got to look back up here first. It's like September since we've done this, right? Well, the exam, but. So we look up here. This is positive. So we're in quadrants 1 and 4. Cast. 1 and 4. So x equals 1.3181. And how do we find quadrant 4? 2 pi minus 1.3181, which works out to 2 pi minus to about 4.9651. So I got 2 solutions here and 3 over there. Five of these. That's going to be a big chart. That happens sometimes. Not inadmissible per se, but exactly right. So you're going to be asked to sketch, really, on some interval. Often it's 0 to 2 pi. We're doing 0 to pi because we don't have enough time to do all of it. And sometimes it's negative pi to pi. So consider your interval. And folks, in fact, there's no reason why I solved up to 2 pi. In MHF, it's not like a rule that you solve always between 0 and 2 pi and then cancel out the ones that don't. You solve on the interval that you're given. Usually it was 0 to 2 pi, but remember we did a couple of negative pi to pi's. And once in a while you do 0 to pi. So like, same thing here. I would have only done up to the interval and I would have stopped at pi because 2 pi isn't in the, I would not normally have written it. I wrote it because that's familiar to us and I'm reminding you and I wanted to have it there so we could point out that that is not in the interval. So both of these are not in the interval. How do I know this one's not in the interval? Well, it's in quadrant 4. What is 0 to pi? So anything in quadrants 3 and 4 are no good. Quadrants 1 and 2 is what I would want. So these are not in the interval that we were given. So that's gone, and that would be gone. We wouldn't even bother doing them. If you can, stop at the end of the interval to save yourself the time. Any questions? Okay, the other thing that happened here that's interesting, our interval was 0 to pi. These are the ends of the interval. Which is fine. It means things are going to be a little bit different. This doesn't happen in rational and polynomial expressions. Okay, so things are going to be a little bit different for these kinds of graphs because it gives you an interval. Otherwise, you'd be graphing infinitely. It would have an infinite number of turning points because it's periodic. So I'm not going to ask you to graph that. So we always give you an interval when it's trig. So these are the ends of the interval, so it makes it a little bit different. So let's see what that looks like. I don't need to go below the end of the interval. Normally, we would start at x less than 0, but I can just start at 0 because that's the beginning of the interval that I'm required to be doing my work on. We follow that okay? Does that make sense? Okay, and from there, it's more or less the same. Right. There's no reason to. 0 less than x less than 1.3, 1.3, 1.3 less than x less than pi. And again, pi is at the top, the other side of the interval, so I can just stop there. The ends of the interval are not always in your chart. Often they will be in one of the charts somewhere. So you got to know what to do when that happens, but it doesn't always happen. It's not a rule that it always happens. Just so happened that they came out as solutions, and that was the interval that I gave you. Okay? But they are solutions. They're not where it doesn't exist. They're where the derivative was equal to 0. I take my calculator. I pick whichever version of the first derivative that I want, this one. Or maybe like this is another version of the first derivative. And if you're doing it a whole bunch of times, you might program your calculator with that function so you can just change the variable value. In my first interval, I have the number 1, so I'd probably type 1 in. So I'd probably just do like 4 sine 1 cos 1 minus sine 1. In the last unit, we would just do that by inspection. Just look at the factored form. Can you tell if this is positive or negative by plugging 1 in? Like in your head? No, I don't think so. Can you tell if this is positive or negative by plugging 1 in? I don't think so. Not generally speaking. Generally speaking, you are maybe once in a while you could if it's just sine times cos. But generally speaking, we're actually putting these in our calculator. So that programming trick of programming the function or the derivative or the second derivative into your calculator will save you a lot of time, especially if it's a long chart. I'm only doing 2 in this case. So I already have the answer, so we're going to bypass this. But you'd plug it in and make sure that you get something. For this one, I get a positive. For this one, I get a negative. What does that mean this is? What's happening here? Changes from positive to negative. So this is increasing. Not point of inflection because this is first derivative chart. This is decreasing. So this is a local max. Good. And we'll find that point. We were asked to do a first derivative chart. If you're asked to do that, you'd find the point here. I'm going to write it down, but we're going to do it after as well. So this is 1.3, 1.125. What's happening here? It's going up after. It has a derivative of 0 at that point. So how do we interpret it? How do you know? What if it was increasing before as well? So we don't know because we didn't test in the area before. So that's fine. So all we can say is this is some kind of horizontal tangent line. Don't know anything else. You don't have to write this every time. I'm writing it for our note. Same thing here. We don't know. When you're doing a sketch, it doesn't matter. You're just going to sketch it as a horizontal tangent line. And it doesn't matter if it goes down afterwards or up because we're not sketching past that point of the interval. So generally speaking, we don't care what those are either. We don't need to worry about it. Does that make sense? Okay, I think that part's done. We are going to move on to second derivative. I'm just rewriting these. so I can refer to them. Okay. So, we good? We were asked to do a first derivative chart and a second derivative chart, so we're moving on. We had sort of three different forms, I guess you might say, of the first derivative. This was what we got when we just took the derivative and simplified, but in order to solve, we did a swap out and then factored it. Which of these three forms is the best one to take the derivative of? Well, that's kind of up to you. These both have product rule in them, so I think this one's the easiest. Usually that's what happens. You go back to this one where you're just adding, subtracting things, avoid product rule, I think is the rule of thumb here, but there's some maybe area for discrepancy. We're taking the second derivative. Derivative of sine is cos, so this is going to be cos of 2x, and then I take the derivative of the angle, so I'm going to do that all in one step and take that out, multiply it by 2 here. Hopefully you follow that. Derivative of sine is cos, so minus cos. Y prime exists for all x. Y double prime mean? So where does y double prime equal 0? When 4 cos 2x minus cos x equals 0. Again, you might do all of that factoring and prep work before when you're doing a sketch. So our order is a little bit different here, but it doesn't really matter. How do I solve this one? Not yet, because they have different angles. So you can't factor that yet. Yeah. Yeah, we got to do another swap out to get the angles the same. What are there's 3 versions of cos 2x. Does anybody know any of them? Yeah. That's very close to one of them, but it's not the one we want, because then I would have a sine and a cos, a sine squared and a cos, and I'd have to do another swap out. What was it missing? They're very close. That's cos squared, but it's actually 2 cos squared. Minus 1. Doing a little bit of work here. I've got 8 cos squared x minus cos x minus 1 equals 0. What is this? Yeah, thank you. What is this? A tricky trinomial. B squared minus 4ac, I believe, worked out to 129. Don't roll your eyes at me. Yeah, this one's a bit of a disaster. So we got to go to quadratic formula. Be very careful. This is not x equals. This is cos x equals. I'm going to write this out. Negative b is negative 1, so 1 plus minus the square root of negative 1 squared minus 4 times a times c all over 2a. But at this point, you can go, I'm going to say, I'm okay because these are so long. You don't even have to write that out. Now, if you make mistakes, to be careful, you might. If you've already done the discriminant, you could just, and you're sure that you did it correctly, which is pretty easy, but you could just put 129 in there. I don't care. Or you could even say cos x is approximately 0.77 radians. Cos x is approximately negative 1.19 radians. And then you would say by quadratic formula. Give me that. That'll be enough. But you make sure you don't make a mistake there. You make a mistake there, you rush through that, you got your POIs all out of place, and you know how hard it can be to graph when you've got something out of place. One little mistake in that could make a big difference in where those values end up, right? Okay, again, we're only doing 0 to pi, so generally speaking, we would have, from 0 to 2 pi, we would have two values for each of these. So x related is 0.69. Oh, radians. That wasn't radians. That was not radians yet. This is radians. And x related is 0.87. When you put this into your calculator, you do not put the negative in. Shift cos 1.19. Even better if you can do exact from this. So find this value, then do shift cos and write that down. Find this value, shift cos and write that down. Generally speaking, you have two solutions, but we're only doing quadrant 1, quadrant 2. So this quadrant 2, because it was negative. Again, folks, pay attention. This is negative. So this one is the related angle, but I want quadrant 2 here. How do I find quadrant 2? Pi minus. Which works out to about 2.27. Nowhere did the second derivative not exist. I've got two solutions where the second derivative is equal to 0. Second derivative chart. Remember what I said before? You don't always have the ends of the interval in your charts. This is a clear time when we don't. Don't you agree? So why would it not make, I'm not going to do this. Why am I not doing this? Huh? No? This is the right value that I want. I want 0.69 as my first value. No? Why? Yes, that is what we're going to do. But, you know, if you got away with this, as long as you check the value close to this, you'd get away with it. But why is this wrong? The next place where it changes. If I chose negative 10 to represent this interval, who knows how many times the graph has changed before it gets to negative 10. So you can't just do less than. So Daniel's right, we need 0, and I'm actually going to include that point, less than or equal to x, less than 0.69. Then I got 0.69. Then I got 0.69 less than x, less than 2.27. Then I get 2.27. Then I get 2.27 less than x, less than or equal to pi. Again, I don't want to go beyond the ends of the interval because I don't know what's happening after that because I haven't checked. I don't know what the next value is. We didn't bother solving for it. So you got to just stop there so you know where to pick your values to test your intervals. Now we're looking at the second derivative, punching that into your calculator possibly, programming it in, checking 3 values. I'm going to sidestep that and put them in here. I would check maybe 0.1 for this interval, and it works out to be positive, I would check maybe 1 or 2 for this interval, works out to be negative, and I would check 3 for this interval, turns out to be positive. So this is concave up, concave down, concave up. So what's happening here? That's our POI. What's happening here? Another POI. I'll call this one A. It's 0.69, 0.58. Call this one B. It's 2.27, negative 0.47. And remember C, it was 1.32, so it's in this interval. And that would make it, in concave down, would make it a local max. That's the end of the expectations for that question, but I want you to watch. I don't even know that you want to try to copy this down. This is what we're going to do tomorrow, but just to give you a little bit of a prep. The next thing we would have to do when you're sketching is we haven't done this part yet. We could find this point. We don't know what it is, but we could find the point, which you would have been required to do, but I skipped it because we're going to do it next. When you're sketching, part of your sketch requires you to find the start point and the end point. You might find it because it's an interesting point, or it might not be an interesting point. So you have to find it anyway. So my start was 0, and apparently it starts at the origin, and my end was pi and negative 2. Brad, you have a question?
Yeah, I was just going to ask, are there any questions where we have to do charts?
Not likely. No. I'm going to sketch it just because we have all the information. We might as well start to look at what these are like. Not required for the homework tonight. Was not part of this question. But there's a lot of details going on, as you can see. There's sometimes going to be a lot of maxes and mins and a lot of points of inflection. So I start at 0, 0. I have a point of inflection that comes first. That's point A at 0.69 and not very high. And then I have a max that's somewhere up here. And so if that's at 1.3, this is going to be around 2. At 2.1, I have another point of inflection, and then 3, that's 2, so 3 is going to be right around here, so pi is going to be right around here, and that's the end. So this comes around like this, inflects here, and it's concave up there, but I don't know if it's but it's changing. So it's either going down or it's turning back up, but we don't know. Then it comes down, it's concave. Ooh, that wasn't very good. So it's coming around and it's concave down, and that's where it inflects to concave up. And then it goes on, and again, this is, I believe, just happened to work out to be a horizontal tangent, but I don't know what else is going on there. So this was point of inflection A, this was point of inflection B, and this was local max C.